Hey everybody, welcome to the last video in our triangle congruence unit, which is video 6.3 here. We're going to be talking about the hypotenuse leg congruence theorem, and just for this last congruence theorem, I wanted to talk about kind of why it's possible and where it comes from. But first off, just a quick review of vocabulary. Hypotenuse legs is the names of the different sides of a right triangle. Remember, the hypotenuse is always that side that's opposite the right angle, or the longest side. And then the two sides that come together to form the right angle are what we call the legs. So that's here and here. So, just a quick review. We've already learned 4 ways to prove that triangles are congruent, 4 shortcuts that we have already. We started with angle, side, angle. We went to side, angle, side. We went to side, side, side. And in the last video, we talked about angle, angle, side congruence theorem. Now we're going to talk about the final congruence theorem in the big 5 here for congruence, and that is HL, or hypotenuse leg congruence theorem. So it's a special case that can kind of be proven from the other ones in a way. If the hypotenuse and the leg of a right triangle are congruent to the hypotenuse and the leg of another right triangle, then the triangles are congruent. That's the HL theorem. So in example 1, we're actually going to prove that. So first off, given that triangle ABC and triangle DEF are right triangles, where C and F are the right angles in those triangles, and also given that AB is congruent to DE and BC is congruent to EF, what we're asked to prove is that the triangles are congruent. So if we were to just go around the triangle and make this into a shortcut, this might be considered a side-side angle shortcut, or in other words, a 2 sides and a non-included angle shortcut. But if you look at the 4 we've come up with, that's not one that we've worked with. And there's a reason for that. There's only one special case where side-side angle works, and that is when the non-included angle is 90 degrees. So what we're going to do here, because we know these are right triangles, we know that the Pythagorean theorem applies. So on the left-hand triangle, we have a squared plus b squared equals c squared. And in the right-hand triangle, the way that they're labeled here, you can see we have d squared plus e squared that equals f squared. Since it's given that AB and DE are the same, that means that actually C and F are the same. So we're going to re-substitute C and F as equal quantities, which means that if the right-hand sides of those equations are equal, then so are the left-hand sides, which are a squared plus b squared equals d squared plus e squared. Then the second congruence statement we have is that BC is congruent to EF, or in other words, A is congruent to D. So if A is congruent to D, we're going to substitute into D for the above equation, so we get a squared plus b squared equals actually a squared plus e squared. Again, just making that substitution there that D and A are the same. Then if we subtract a squared from each side, that shows that b squared equals e squared, and taking the square root of each side, b equals e. So what we can prove is that the third pair of corresponding sides are also congruent, or AC is congruent to DF. So therefore, the triangles are congruent by, in this case, side, 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 triangle congruence theorem, which resulted directly from the HL triangle congruence theorem. And so that's just kind of shows you where HL, the triangle congruence theorem that we have stated in the box above on page 296 here, could also follow from another one of our triangle congruence theorems. So on the your turn, Number 3, notice we're just basically kind of seeing if there's enough information to prove that the triangles are congruent. Well, if we have that triangles here have vertical angles at VZW and YZX, then this is going to be an angle-side congruence theorem. And again, that's with our vertical angles. So that would be yes. Sorry, just thought I'd do that one for you. Get a little harder on the next page with proofs. So let's see what we can do here with explain 2. All right, in explain 2, we're just going to walk through a couple of proofs using the HL theorem. Really, it's important to just know how to mark these diagrams. So given that angle P and angle R are right angles, those are already marked, and that PS is congruent to RQ, what we're being asked to prove is that these two triangles are congruent. So P and R are right angles, given. PS is congruent to RQ, also given. Notice though, we've got a shared side here between SQ in one triangle and SQ in the other. And that is also, shared side is always a reflexive property of congruence. Don't forget that. So now we can justify that the triangles are congruent by the HL triangle congruence theorem. And if we look at the statements, we can see kind of which part is which. This is the part that deals with our angles. PS is and RQ are our legs, and then SQ is our H. So there's our HL there. Okay, again, we need a right angle, a hypotenuse, and a leg in order to prove HL. Let's look at part B. Given that J and L are right angles and that K is the midpoint of JL and MN, what we're being asked to prove is that these two triangles are congruent somehow. So the first one, of course, is the reason is that it was given to us, and then that was given to us as a second statement as well. How are we going to prove that JK is somehow congruent to KL and that MK is congruent to NK? Well, we were already told that K was the midpoint, so this is just the definition of midpoint. So now look at what we have here. Here's our right angle. And we have JK and LK, that's our leg. And MK and NK is our hypotenuse. So now we have triangle JKN is congruent to LKM. Why? Because of the HL triangle congruence theorem. I want you to take a look at your turn number 5 here, and it says use the HL congruence theorem to again write a proof that the triangles are congruent. I might remind you to redraw the overlap triangles separately before you begin the work on this proof, and make sure that you're doing a 2-column format. Okay? Let's see what you guys can do with that one, and we will see you in class.